In this video we're going to start a new topic of quadratics, and today we're going to look at discriminant. Now, we looked at discriminant in National 5, so we're going to look at some revision of that in this lesson and taking that a little bit further as well. So just a reminder then, if you have a quadratic equation of the form ax squared plus bx plus c equals 0, the discriminant is defined by b squared minus 4ac. Now, if we calculate the discriminant and it's positive, that is, it's greater than 0, we might have a graph that looks something like this. So you can see here that this curve, this parabola, cuts the x-axis in two places, meaning that we have two real and distinct roots. If b squared minus 4ac is equal to 0, we might have a graph that looks something like this. So we can see that we have a turning point there that is also a root because it's cutting the x-axis in one place. So we have one real and equal root. We would also call this a repeated root. And finally, if we have b squared minus 4ac being negative, that is less than 0, we could have something that looks like this. And you can see here that that curve, that parabola, does not cut the x-axis at all, and therefore there are no real roots. So let's have a look at an example, and like I said, this first example is revision from last year, from National 5. So we want to find the nature of the roots of the equation yx squared plus 21x plus 16 equals 0. So the solution then, we firstly need to pick out our values of a, b and c. So ax squared plus bx plus c. So that means that a is 9, b is 21 and c is 16. So calculating the discriminant then, we've got b squared minus 4ac, that is 21 squared minus 4 multiplied by 9 multiplied by 16. And when we calculate that, we get negative 135. So we then need to make that comparison. Is the discriminant greater than 0? Is it equal to 0? Or is it less than 0? And we can see here that 135 is negative, so therefore it is less than 0. And that means that the nature of the roots, well, there are no real roots. And we can check this using a graph. So if we plot the graph, we get something that looks like this. So that is the curve 9x squared plus 21x plus 16 equals 0. And we can see here that it does not cut the x-axis. So there are no real roots. Just now would be a good time to pause the video and copy this example down in your notes. Now, example 2 then. And example 2 involves some unknown terms in the quadratic equation. So it's almost like looking at example 1 but in reverse. So in example 1 we were asked to find the nature of the roots, but this time we're going to be given the nature of the roots and work backwards to find one of the values of a, b or c. So we want to find the value of q such that 6x squared plus 12x plus q equals 0 has real roots. So you can see here the nature of the roots is that they are real, and we need to find the c value, which is currently q. So we'll firstly pick out our values for a, b and c. So a is 6 in this case, b is 12 and c is q. Now, for that equation to have real roots, if it was two real and distinct roots, we would need the discriminant greater than 0. And if it was one real and equal root, we would have the discriminant equal to 0. So that means that here, that both of those cases are applicable. For real roots, we want b squared minus 4ac to be greater than or equal to 0. So we can have both cases involved in this. So substituting in, we'll get 12 squared minus 4 multiplied by 6 multiplied by multiplied by q is greater than or equal to 0. Simplifying gives us 144 minus 24q. And obviously you can solve this two different ways, but I am going to subtract my 144 from both sides to give me negative 24q is greater than or equal to negative 144. And then I'm going to divide throughout by negative 24q to leave me with q on the left hand side, and that will give me q less than or equal to 6. So just remember here, if you are dividing throughout by a negative and you have an inequality, the division by a negative, or multiplication by a negative for that matter, reverses the sign. So it reverses the inequality sign. So q less than or equal to 6 is our final answer. And just before you copy this down, we're going to have a wee look at the graph here. So that is, if q was equal to 6, we would have one real and equal root. And if q is less than 6, you can see here some of the values less than 6, and all of those, when that moved there, had two real roots. Now, what happens though if q was greater than or equal to 6? Well, we can see here that it would have no real roots. So you can see the difference that inequality would make there as well. Okay, so just now would be a good time to pause the video and copy this one down in your notes before coming back for example 3. So, example 3 then, we want to show that 2k plus 4 x squared plus 3k plus 2x plus k minus 2 equals 0 always has real roots. So this is a proof this time. It's saying show that, and we want to show that the discriminant is always going to be greater than or equal to 0 because it's saying that it's always got real roots. So the solution then, we want to start with b squared minus 4ac. So we need to pick out our values for a, b and c here. So you can see that a is normally the coefficient of the x squared term, so that's 2k plus 4. B is the coefficient of the x term, which is 3k plus 2. And c is the constant term, in this case k minus 2. So substituting into b squared minus 4ac gets us 3k plus 2 all squared minus 4 times 2k plus 4 times k minus 2. Expanding our square bracket here will get us 9k squared plus 12k plus 4 minus 4 multiplied by, now I'm going to expand these brackets first and then I'll multiply by the negative 4 later. So expanding these brackets here gives me 2k squared minus 8. And now I can expand this. So that gives me 9k squared plus 12k plus 4 minus 8k squared from here, and then plus 32 from the negative 4 multiplied by negative 8. Now, I can obviously simplify this expression here. So I've got 9k squared minus 8k squared, leaves me with k squared. I've got my 12k, and then I've got a 4 plus 32, which gives me 36. So you can see the simplified expression is k squared plus 12k plus 36. Now, I want to show that this always has real roots. I want to show that it's always going to be greater than or equal to 0. And if you remember back to a previous lesson, when we talked about increasing and decreasing functions, we talked about how if you're trying to prove that something is always greater than or equal to 0, then we are looking for a square, because we know that a squared term is always equal to 0 or always positive. So that's really what we're wanting to find here. And I can see that k squared plus 12k plus 36 is actually a square if I factorise this. This will give me k plus 6 all squared. And like I said, if you're squaring something, you know it's either going to be equal to 0 or positive. So k squared plus k plus 6 all squared is greater than or equal to 0. Therefore, always has real roots as required. And again, we'll just have a quick look at the graph. And I'm just changing the value of q as I go here. So when I play this, the graph is going to move around as the value of, I think I said q there, as k changes. The value of k starts to change here. Oops. And you can see it's always got those real roots. It's either got one root or two roots, just depending on the value of k. So just now would be a good time to copy down this example, pause the video before the screen goes blank, and take this down in your notes.